All right, everyone, we're back, and we are going to go over our next homework assignment and how to work through each of these problems. So we're just going to start with this one, 4.1d first. For 4.1d, we start off with t of n equals 7t of n over 3 plus n squared. So first, we just we pull out our values. So we have a is going to equal 7. We have b is equal to 3. And we have f of n is equal to n squared. Now we do know that we are just going to plug in b and a into log b of a, which is log 3 of 7, which ends up coming out to 1.77. So the master theorem tells us, because we know that f of n is in 2, we know that our log 3 of 7 is 1.77. So we know that to get to 2, we're going to need to add. And because of that, the master theorem gives us f of n is equal to big omega in log b of a plus epsilon. So we know that to get to f of n is n to this squared. So we know that we're going to need to add 0.23 to 1.77 to get that to be to equal. So we end up with the third case, which is we know that t of n is big theta f of n. So then we go and we substitute, and we end up with we substitute for f of n, so we find out that t of n is equal to big theta f of n, which is just big theta n squared. So that is all for that one, and we know that that is our asymmetric upper bounds is big theta n squared. So that was 4.1d. So now we are going to go to one of the next problems. So now we will go to, let's see which one we got here. We'll go to 4.1f. So this problem is t of n equals to 2t n over 4 plus the square root of n. Now we're going to do the same thing as we did the first problem. We are going to pull out our variables. So we have a is equal to 2. We have b is equal to 4. And we know that the square root of n is equal to f of n is equal to n to the 1/2. So now we plug in a and b into log b of a, which is log 4 2, which equals 1/2. So now if we know that n of f of n, which is n to the 1/2, and we now have our log b of a, which is 1/2, which we know are equal, we do not need to add or subtract. So then we go to look at the master's theorem, which tells us, which is going to be the second case, that f of n equals big theta in log b of a. So then it also tells us that t of n equals big theta in log b of a log n. So now we're going to go in and we're going to substitute. We have t of n is equal to big theta in log 4 of 2 log n. And then we have our final conclusion that t of n equals big theta into the 1/2 log of n. So now we'll move on to the next one. I'm going to pull that one up real quick. So next we will do 451. So for this one, the problem is T of n equals 2t of n over 2 plus n to the fourth. So once again, we're going to pull out a equals 2 and b equals 2 and f of n equals n to the fourth. So now we're going to plug those a and b variables in to log b of a. So we have log 2 of 2, which equals 1. So we know the Master's theorem tells us that f of n, big omega, is n log b of a plus epsilon. So the way we know that is we see that f of n equals n to the fourth, and so we need to make sure that that equals. So we know that we're going to have to add 3 to the log b of a. So we know that epsilon will be 3, and the Master's theorem tells us that t of n equals big theta f of n. So then we just substitute, and we have t of n equals big theta f of n, which then goes to t of n is n up to the fourth, is the arithmetic running time. So now we'll go on to the next example. Let's see here. Give me just 1 second. I'm going to pull it up. All right. So now we're going to work on 4.51 B. So this one we have t of n equals 2t n over 4 plus n. Let's see here. To make sure we have not done this one. Okay. All right. So for this one, sorry, I'm making sure we haven't already done this one. I don't think we have. So for this one, we have 4.51. T of n equals 2t n over 4 plus the square root of n. We know a equals 2, b equals 4, and f of n equals n to 1/2 because we know the square root of n is 1/2. So now we're just going to plug and play. Log b of a equals log 4 of 2, which equals 1/2. And so there we see that the square root of n, like we said, f of n equals n to 1/2. So we know those are equal, so we know it's the second case. So from the Master theorem, we get big theta n log b of a. Then we get t of n equals big theta n log b of a log n. So now we just substitute. We have t of n equals big theta n log 4 of 2 log n. And we get our final answer, which is the arithmetic running time of big theta n to the 1/2 log n. So now we will move on to our next example. We have 2 more left. So now we'll work on 4.31. So 4.31, we have t of n equals 4t n over 3 plus n log n. We know that a equals 4, b equals 3, and f of n equals n log n. Now, because this one is a little more difficult, because what f of n is equal to, it's harder to make sure that f of n is equal to one of the three cases in the master theorem. So, but we'll start off the same way. We'll plug and play a and b. So we have log b of a is equal to log 3 of 4, which is equal to 1.26. Now, the way I figured this one out was we look at f of n, which is n log n, and the main variable there that's going to affect the growth is n at the beginning, which is technically n to the first. So we can think of that we need to get that 1.26 to equal 1. And the way we found that out was basically graphing that. So because f of n equals n log n, the main value is n, like I said. So we need to subtract 0.26. So we're going to say that epsilon is equal to 0.26. And we just use the master theorem. And we have f of n is equal to big O of n log 3/4 minus epsilon. So therefore, our final answer at the asymmetric running time is t of n is equal to big theta n log 3 of 4. Now, we will move on to the last problem. Let's see here. Give me just 1 second. All right, 4.31. So for this one's a little different than the other ones. So we start off with t of n is equal to t of n minus 1 plus n. And we're just gonna guess that it's a big O of n squared, which is the correct answer. But the question has us assume that t of n is less than or equal to cn squared. So first of all, we set Tn is less than or equal to c of n minus 1 squared plus n. And what we did there was we just basically plugged in the n minus 1 in the c of n squared. So now if we look at the next line, we just basically are going to continue working this out. So we square the n minus 1. So we have c n minus 1 times n minus 1 plus n. And now we have c of n, and then we multiply those, and now we have c of n squared minus 2n plus 1 plus n, which then multiplied out equals c of n squared minus 2n plus c plus n. So at this point, we're going to get rid of the constant c. We're going to assume that c is equal to 1, and we find out in the end that ends up working out. We have n squared minus 2n plus 1 plus 1 plus n, which now we go down to the next line, and we have removed 1 from the n, so we now have n squared minus 1 plus n, which then reduces down to n squared minus n minus 1, and our final answer is going to be less than or equal to n squared. And the reason that is because we know that n squared minus anything is going to be less than, we know that n squared is going to be the asymmetric upper. And we also find out that the inequality holds for any n that is greater than 1. So then we come to find out that t of n does in fact equal big O of n squared. So we were able to solve that. And like I said, the way we know that, we got down to n squared minus n minus 1. But because we know that n squared is the bigger piece there, and that anything minus n squared, we know that, so that it's going to be less than or equal to n squared. So it can't, there's no way that it can be any bigger. And that is our last problem. So I hope everyone enjoyed, and thank you for watching.